Is that?
I should be able to do it Friday.
You should be able to do it Friday? Okay.
If that's okay with you, I don't.
That's okay with me. No. We can try for Friday. That's all good. We can aim for Friday.
Oh yeah, I'll let you know what my break is because actually I'll probably come to class given that it doesn't need my computer.
Right.
My spring break is flying every day in Texas, so.
Right.
I may be there, I may not, I don't know.
Well, maybe we can. What would be cool is if we could get started on that Lie algebras thing. But let's see here, an orthonormal. So I was talking. Well, let me focus on this for now. Orthonormal sequence xn in a inner product space E is said to be complete. That seems like a bad word to use here. If for every x in E, we have x is equal to its Fourier series. Woohoo! N equals 1 to infinity of x with xn, xn. What is wrong with these people? Goodness gracious, Audric, you just don't even know. It's really loud today. I mean, if there was drinking on campus, I could understand it, but there's no, as far as I know, now that a certain person's gone. But anyway, let's see here. So an example would, of course, be given by the previous example. This is not complete because its cosine is definitely in L2, and yet that did not reproduce cosine. He says, it's important to remember the right-hand side of the equation I just wrote is an infinite series. The equality means, what does it mean? This means that we have the norm of x minus the sum, let's say k equals 1 to n of x with xk, xk. This is going to 0 as n goes to infinity, right? That's what's meant. In other words, the sequence of partial sums has to converge to x. In fact, I'd usually write typically I would, in any other context, I would flip, I would usually write the sequence of partial sums minus the limit. I don't know why I'm doing it the other way now, but it's the same, you know, but yeah. So he says, oh, okay. Huh. He has an example here, and I'd like to write down the example, see if I can understand what he's saying. It's abstract, though, yeah? So it's kind of a little bit, I don't quite get what he's driving at here. So looking again at E equal to the square integrable functions on minus pi to pi with Fn orthonormal sequence, right? He doesn't tell us what it is. He doesn't tell us what is the orthonormal sequence. Then by, he's elaborating on what I wrote and read above. okay, then if we say f is equal to the sum n equals 1 to infinity of the inner product of f with fn, what does that mean? It means the limit as n goes to infinity, right, of the integral from minus pi to pi of the absolute value of f of t minus the sum k equals 1 to n alpha k fk of t squared dt, that is equal to 0, and where the alpha k is what? The so-called Fourier coefficient alpha k is equal to the integral from minus pi to pi of f of t f bar k of t dt. And he mentions that we cannot claim, we cannot from this, even if it was the case, right? Like it's not the case for the sine sequence, right? If you have all of this, then you don't get to say as much as you'd like. You'd like to say f of x is equal to, right, you know, the sum of, you know, alpha k equals 1 to infinity. Well, let's say alpha n. Fn of x, right? You can't. Why can't you say this? Not quite. Because remember, the integral doesn't imply pointwise convergence. We can have that those two things are equal almost everywhere, but we don't have equality everywhere necessarily. If this all happens, we just get, so like what that actually means is that like if the if you do have a complete sequence and you've calculated the Fourier coefficients for a given function in L2, then you do have that the Fourier series matches it most places. But there could exist a finite set of points where it disagrees. Where that typically happens is discontinuities in the function. And I'm sure we'll get to that eventually here. So definition, orthonormal basis. What is an orthonormal basis? An orthonormal system B, an inner product space E, is called an orthonormal basis if every x has a unique representation like we're doing right now. So, definition, xn, orthonormal. I think it has to be complete, right? Orthonormal basis, an orthonormal, well, okay, orthonormal set, or I guess he says, he's back to system again. An orthonormal system, B, is called orthonormal basis. Good grief. Orthonormal basis for the inner product space we're looking at if every x in E has unique representation x is equal to the sum n equals 1 to infinity of alpha n xn, all right, where alpha n are complex numbers, and xn are distinct elements of B. So, oh, here it is. I mean, this is the thing I was wondering about. How are we going to make basis, how are we going to extend the concept of a basis to infinitely many things? Well, I mean, no, goodness, we have infinite bases before. So this is, I don't know. Oh, I guess we're allowing, so like usually, okay, previously, here's the deal. In linear algebra previously, we talk about basis being a spanning set, a generating set, right? But it was with respect to finite linear combinations. We are not assuming a finite linear combination here. So we extended the spanning concept to series now for this context. So we've left the realm of linear algebra proper. So he says, note that a complete orthonormal sequence is an orthonormal basis. So it suffices to show uniqueness. All right? So I think we're going to need another day. Sorry, guys. This is a long section. This is a long section, guys. Yes, it is. This is probably maybe the most important section in the whole book, honestly. So we'll pick up here next time and prove the uniqueness of the orthonormal basis, right? We'll prove that complete orthonormal sequence is an orthonormal basis because the representation has to be unique. That's what we have to prove. So like the spanning is given by the definition of a complete, right? So it suffices to prove uniqueness. I guess we could do that much, right? It's just me who's tired. You guys aren't tired. So let's do that much. So let's suppose you have a complete. Let me do it over here. So suppose you have a complete orthonormal system, right?
Yeah.
Let's prove it's an orthonormal basis. So suppose xn is complete orthonormal sequence. All right. Let x be an element of E. Then we have what? That x is equal to the sum n equals 1 to infinity of the inner product of x with xn, right? That's by the definition of complete that's right there. So we picked an x and we showed it has a representation, right? These are complex numbers. So all that remains to do is what? Yeah, we need to show uniqueness. So suppose that x was equal to the sum, n equals 1 to infinity of alpha n xn. Our goal is to show that alpha n is equal to what? Mm-hmm. So let's see here. So we know that we have S n equal to the sum k equals 1 to n of x with xk, right? And that goes to x. as n goes to infinity, right? In terms of convergence and norm, right? But we also know that S, let's say alpha n, which is the sum k equals 1 to n of alpha n xk, alpha k xk, right? Goes to x as n goes to infinity. So if we look at Sn minus Sn minus Sn alpha, we literally have the sum k equals 1 to n of alpha k minus, or excuse me, the inner product of x with xn, xk rather, minus alpha k times xk, right?
Then all we have to show is that it goes to 0.
Well, we know that this goes to x minus x, which is equal to 0, right?
Yeah.
I mean, because of that. So then, of course, we can throw some norms on this thing, right? So this implies that the sum k equals 1 to n of the absolute value of xk minus alpha k squared goes to 0 as n goes to infinity. I've probably written too much. There's probably a simpler way to show this. I could probably look at the book. That would be smart. Oh, he's doing it for alpha and beta. But yeah, it's the same proof. Okay, I don't feel bad. And so the only way that that can go to 0, right? So here you're looking at what? A sum of squares, right?
Yeah. Oh, so
Yeah.
they're always.
And so that implies that x with xk must be equal to alpha k for all k equal to 1, 2, right? Which is to say that, in fact, alpha k is exactly the inner product of x with xk, right? There's a more low-tech solution here, though, which is just to say it's already unique. Why is it unique? We have a formula for it, and the inner product of x with xk is not up for debate. It was already manifest that the formula was unique. Way back here. This proves uniqueness, in my opinion. There's no debate about the representation.
Two different inner products. Is
Yeah, I mean, given an element, you're given the sequence, they're in order, the order of the sequence is not up for debate. These numbers are fixed numbers for each k, for each n. The representation's unique. Like, I don't really need all this, but mathematicians tend to do this. They have unnecessary proofs of uniqueness in places because, mathematicians really like to prove uniqueness, like a lot. so it's I guess all the mathematicians are like millennials or something. They want to be unique. I don't know. That sounds wrong. We might question it. Diversity is our strength, right? Let's see here. What's this? Where are we? And then, we'll pick back up there next time. I think I better stop here. Is that okay? Okay, so I'll try to pick up right after the proof we just did here. So bottom of page 114. But we are getting closer to the really applied part of this material. See, because if you guys I erased it, but if you guys had already had a course in differential equations, those integrals are actually, those are the integrals that you have to do in order to actually find the Fourier series that give you solutions to like the wave equation and things like that. You build like a sum of sines and cosines to represent a function that Like you have a wave equation, you have initial space, initial shape for the wave. You find, you do those integrals to find the coefficients to build a sum of sines and cosines, which models the wave. But it's exactly that mathematics. Like so we're kind of building a machine to prove or to analyze the issues, the analysis issues of such problems. That's